Hi, ready to help you?
My name is Mike.
And I'm Rudy Yamas, and today we'll be determining the velocity of a sediment plume from a project by Dr. Ruby. So for our problem, sediment plumes can negatively impact the environment by kicking up debris that can get into the gills of fish, as well as disrupt vegetation that can be providing helpful emissions. By doing this, we'll be using image processing. So for our image acquisition system, the video will be provided to us by Dr. Ruby, and the video in question was captured by a Mavic 2 drone used by the university, which was flying high above while students and the instructor were kicking up sediment, allowing for the detection to happen. There were also 2 poles that will be used as a set point of reference for us. For our block diagram, first we're going to have our image acquisition via that drone, then we will move on to masking filtering so we can see an actual estimate of the plume's velocity and direction. Then we will move on to creating a histogram and thresholding for image processing. Finally, with the information acquisition, we will begin to analysis with it, and we will use our velocity extraction.
For our image processing method, we started with the markers. The markers were hard to see in the video, so we connected a red line between them, forming a frame of reference. Then the line was able to give us easier tracking of the plume after the masking, and finally being able to detect the edge of the plume. We'll measure the distance between the end of the edge of the plume and the line frame reference. With the process of image, we started with equalizing the histogram, then filtering the technique provided by Dr. Ruby as we mask the frame, allowing us to see the plume progression easier. Then finally, with the starting and stopping point of the data collection by 2 frames, this will give us a comparison of how fast the plume has traversed. And finally, yes. As you can see here, with the masking, it was easy to tell how far the plume is. And over here, this is our first frame. Our second frame, as you can see, the plume has traversed more towards the right side of the screen, with the following histogram comparing the brightness level of each plume. Here is the original frame for the first frame that we picked, and the markers are obviously hard to see. So again, that line that we have developed and put it to make it easier for us to calculate the progression keep the track progression of the plume. So here is that first frame, and next to it is the frame after the masking. As you can see, the plume is steadily right across the marking, the line that we created. On the bottom here is the second frame that we put 500 frames after the initial. Again, the red giving us a frame of reference, and after the masking, as you can tell, the plume has moved across that stationary lines. For the result analysis, by finding the difference of pixels between the 2 frames and dividing it by the number of frames that we have calculated, which is again 500, we were able to find the plume velocity of 1.05 pixel per frame.
Our global economic and social impacts are that in global impacts, the release of carbon stored in eroded soil can contribute to greenhouse gas emissions, while the loss of vegetation reduces carbon sequestration potential. Economic is reduced agricultural productivity, basically meaning the loss of topsoil due to shallow water erosion can significantly impact agricultural productivity. Social, it is essential to strike balance between the social impact of drone detection and the legitimate use of drones for beneficial purposes, such as aerial photography, search and rescue operations, or environmental monitoring. Environmental impacts. Erosion can lead to loss of vegetation, which disrupts the balance of local ecosystems and reduces biodiversity, causing habitat loss and biodiversity decline. Ethical impacts are intergenerational equality. Failure to address plume sediments adequately can result in a diminished natural environment, reduced resource availability, and compromise quality of life for future communities. Our health and safety impacts. Our plume sediments can contribute to the degradation of water quality. Sediments can carry pollutants, chemicals, harmful bacteria, leading to contaminated water sources. Our conclusions and recommendations are: our project was successful in identifying the sediment plume using image processing. Once the plume was masked, 2 poles were used as markers to create a static point of reference that determined the distance traveled over the remaining frames. Recommendations for the project would convert the pixels to scale to a real-world measurement, so that we don't use pixels per frame so that we use meters per second instead of pixels per frame, like feet per second. Here's the references.
Thank you.
Guys, today we're doing the MATLAB demo for the live plume detection. As shown here, we are going to run the video frame by frame. As you can see, this here is the frame by frame for the first frame of the video. So when I press pause or start, it's going to go frame by frame. As you can see, these are the number of frames being passed per frame. As you can tell here, the plume is the plume is being generated by students walking back and forth in the shadows water, and in the original frame on top you can barely see the plume, but after a masking provided by Dr. Ruby, the plume is actually easier to see below here. So the code, it started at 1. 1 would be our reference frame for our calculation for velocity. The code will run into about frame 500. The frame number is arbitrary because the first frame is already inputted into a variable, and then once we reach to 500, it is also going to put into a different variable. Using those variables, we will be able to calculate the difference in pixels, and given that the pixels divided by the number of frames that has passed will give us our velocity. As you can see, the frame is continuing, and the frame number is arbitrary. We can pick any frame that we wanted. It's just after 500 frames, it gave us a really good distinction from where the plume started and where the plume ended. Our first challenge in calculating the pixels was determining the stationary markers. As you can see here, there are white dots on the first frame. Those white dots are the stationary markers. It was hard to see, so in MATLAB we were able to establish a line connecting them two, and you'll see that a little bit later in the demo. So we're almost done here. It's almost to 500. Once it reaches to 500, it's going to pause, giving us the frame that we're going to use, and it's going to stop now. As you see, it pauses, and this way this will capture the frame here and it's put it into another variable. As I press play, it will continue for the rest of the frames. This total video has about 700 frames we were able to get. Once the code for the frame by frame is done, it will take the 2 frames that we have selected, and it will calculate the pixels and give us our velocity. There we go. As you see, once it was all done, the frame was done. So we have 2 frames here. So frame 1 and frame 2 was captured earlier. As you can see, that red line there to indicate the plume, a frame of reference for the plume. Since the picture isn't really, it's really hard to detect the plume, so these were also generated in order to make a better, oops, where did it go? Oh, here it is. Oops. There we go. So as you can see above, frame 1, right, the plume is just starting off, and then frame 2, which is frame 500, you can see a significant has advanced. And in MATLAB, the plume velocity was 1.05